Simon.
Okay, Rob's a colleague of mine from Google Australia. He's been working on a couple of the major projects that we've had going here. He's a long-time Googler, been an engineer with Google for, I think, 10, 11 years. Before that, he was at Twitter. And he's also done some research as a research scientist with Telstra, the telecoms organisation here in Australia. He's a UNSW mathematics and engineering, software engineering graduate. And I'm pleased to say that not only is he amongst my colleagues, he's amongst my friends. So over to you, Rob.
Simon, thank you for that lovely introduction. I used to work at Google's New York office, working on speech recognition, and I can confidently.
I forgot that one. Sorry.
I can confidently say that we didn't really talk too much about the mechanics of a cochlea and what happened with audio once it reached the inside of an ear. And in particular, I really enjoyed this chapter in Dick's book because it put together a part of biology and really mechanics and electronics and physics and computing in a really great, entertaining way. To me, the book's title is Human and Machine Hearing, and it feels like this chapter put everything together. Most of this chapter is about, in my mind, is about understanding how the cochlea works. And there's a couple of wonderful quotes from earlier in the book. One of them, I'm actually paraphrasing Dick from a previous presentation, which really stood out. The first quote is really from George Berkashi, where he says, dehydrated cats and the application of Fourier analysis to hearing problems have become more and more of a handicap. And this in particular was really important in that some of the key understandings about how the cochlea works have only been understood once we were able to observe through experiments how a living cochlea was working. And the dead cochlea just didn't behave the same way. And we'll talk about why. Dick's quote from, I think it was the presentation on chapter 11. Dick, I'm quoting you and paraphrasing you. You say, find the simplest model that can simulate what you're trying to model. And that's going to be an ethos that comes through in future chapters, but also in this one. And then the main one that's really interesting is that people were thinking about some of the ways the cochlea works in detail. I'm taking a quote from Thomas Gold from the book. And it's suggested that an electromechanical action takes place where a supply of electrical energy is employed for the cochlea. And we'll talk about how this actually happens in the cochlea. First of all, when we talk about hearing is absolutely amazing. We as human beings hear things anywhere from 20 hertz to 20,000 hertz, which is really a wide range. And even more amazingly, we can hear sounds from 30 decibels to about 120 or so. And that corresponds to a 10 to the power of 9 difference in energy levels. And that's absolutely amazing. We just say, hey, the decibels go from 30 to 120, but the amount of energy difference is enormous. And chapter 14 talks about these two details in particular, where it talks about it to me. And in particular, a framework to understand how this happens. And then we start to talk about how to design a model that simulates a cochlea. My note about this chapter is that this feels like this chapter is an incredible in-depth introduction to an enormous number of topics in computing and in biology. And I felt like I was reading a lot of academic papers that made the jump from this book to me. So it feels like an introduction, but it's really in depth. Oh, I skipped a slide. So overall in picture, I've got a picture of one ear in here. And let's talk about hearing overall. The outer ear plays a role in hearing, obviously. We talk about things like the pinna, shaping the shape of the pinna, which is this on your ear. The shape of that changes and allows more sound to come into your ear. The shape of our skulls also changes things. There's a brief discussion about head-related transform functions in chapter, I think, 22. But that's not the thought for us in here. Overall, sound enters our ear canal via the outer ear and then goes to our middle ear. And the middle ear transfers the compressive energy from the eardrum. So the sound energy, the compressive sound energy from the eardrum via three little bones, the hammer, the anvil, and what's sometimes called the stirrup, or what's sometimes called the stapes. That's another thing that I've learned, which is that there's a lot of multiple names for the same thing in this field.
They pronounce it stapes.
The stapes. Oh, my bad. So not only is the sound transferred from air to a liquid, but because of the different size of the eardrum and the mechanical action of the middle ear, depending on the frequencies, the increase in pressure can be 23 decibels at this point. So the middle ear definitely plays a role in hearing. The other thing that happens in the middle ear, and it's not discussed in the chapter, is that these three bones, they're held together by 3 ligaments and 2 muscles, including the smallest muscle in the body, the stapedius, which is about 1 millimeter long, and either by reflex, which is a reflex in most people, and some people can control it, but we can reduce the action of these 3 bones by about 15 decibels. So we can control the loudness that comes into the cochlea by about that much. That helps explain something like 15 out of the 90 decibels of hearing to me, where we can kind of control that, but there's still a lot to go. So then once we go past the stapes and the stirrup, we come into the cochlea. I haven't found a single picture of the cochlea that explains the cochlea to me. Everything has to come through multiple pictures. The cochlea is sort of a 2.5 spiral little thing. Well, it's a 2.5 spiral liquid filled organ that contains a lot of nerves and what we'll find out is outer hair cells. But if you unroll that spiral and think of it as we have on this, effectively the stapes pushes the liquid into what's the perilymph. That's separated, that goes all the way through the apical end of the cochlea to the other side. These two are called the scala vestibuli and the scala tympani. And there's a very small membrane that separates the two. That on this picture is called the vestibular membrane. Sometimes it's called Reisner's membrane. That effectively has very little mechanical action, but separates out a voltage or a different ionic concentration. So we can talk about this, and what we'll see is that the fluid waves travel through the scala and they deflect the basilar membrane. The basilar membrane motion is detected by inner hair cells. This triggers a neurotransmitter response, and so we hear things. The Reisner membrane separates two fluids with very different ionic concentrations. So if we go through to a slice of what this really looks like, if we look at the little picture on the top right, effectively there's an 80 millivolt difference in electrical potential between the two liquids there. And then inside what's called the outer hair cell, there's an electrical potential of minus 70 millivolts. Oh, I went to the next accidentally. Oh, I didn't go to the next slide. So this means that there's a total of 150 millivolt potential difference. This is actually the biggest potential difference anywhere in the human body. That's written in the chapter, but I couldn't really fit it in here. If we look at the really zoomed in view, we can see what this might look like or what this looks like at a really microscopic level. You'll notice that there are 3 rows in the figure of outer hair cells. That's not illustrative. It really is 3 in mammals, which I find amazing. Mostly. Sometimes I've heard or I've seen a paper or two where for some parts of human hearing, that 3 is in fact 4, but it really is 3. And the understanding of the outer hair cell is basically as follows: that there are stereocilia at the end of the outer hair cell that when there's movement in the fluid, this is oversimplifying things. When there's movement in the fluid, they open a channel for ionic transfer, and this changes the electrical charge of an outer hair cell, and an outer hair cell rapidly changes length with a voltage change. And this basically adds energy and movement to the basilar membrane at that spot. This particular detail is the key for the amplification of cochlear. So I'll mention it again. There's a change in electrical potential of the outer hair cell. This causes a rapid change in outer hair cell length. This adds movement to the basilar membrane, and this is the key for amplification. The basilar membrane movement then triggers the inner hair cell to release a neurotransmitter, which then gets sent to the brainstem. So hopefully this comes out. So looking at this in the microscope, this is from 1987. And so this is from Jonathan Ashmore, and I've sent a link to this, and quoting Jonathan Ashmore, this is an outer hair cell microdissected from a low frequency end of a cochlea, placed on the stage of a microscope. And to change the cell's potential, there's a bit of music added in there, and it's rock around the clock. Hopefully this works over Teams. Let's see.
1, 2, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're gonna rock around the clock tonight. Put your glad rags on, join me home.
Was that movement obvious and visible over the video in here? There's actually a Neil, I'm sorry that it wasn't. I'll keep playing the video for a couple more seconds. Take a look at the top left of the little video.
Put your mouse link.
So there's actually a fair amount of movement in there. That's the actual audio that was playing for the outer hair cell. So that's the movement that then induces further movement in the basilar membrane. Let me go to the next slide. I really had a lot of fun reading about the outer hair cell.
Well, he didn't make a recording of it. He said that he plugged his headphones into the electrophysiology amplifier, but that's not what we heard. We heard the original stimulus, right?
Correct.
Pardon?
We heard the original stimulus, not what came out of the electrophysiology amplifier that he had.
Yes, I think so.
Okay. Okay. Thank you.
So more on this. The way that this change in length was published in 2000. So that's actually relatively recently. And this change in length comes from an electromotile protein called Crestin that came out of a lab run by Peter Dalosh. The figure on the right shows that there's a limited useful range for outer hair cells. The solid line shows the actual output, or the actual way that an outer hair cell functions, where you'll see that it's an asymmetric activation, so that it's somewhat higher than 1 at the end and much lower than 0.5, but not quite. This is typically modeled as a symmetric sigmoid, but it's not quite the way that things work. But it shows that there's a limited useful range. So after really a lot of stimulus, it's almost the same output. And so the best thing to do is to try and keep the useful range of activation of that outer hair cell in the middle. And basically there's an outer auto gain control system, both in biology and in models that we do. The way that all of this is activated, or the way that all of this is, excuse me, there's a notification here. The way that this is actually, how do I put this? The way that this actually works is still an area of active experimental research. So there's an auto gain control from the brainstem that comes back into the outer hair cells. So this is an efferent control of the cochlea from the brainstem. And you can see in the figure on the bottom right that there are neural signals that go into the outer hair cells, and we understand this. There's a paper from 2022 which shows that some of the other cells in the cochlea also have efferent nerve control. And that's Dieter's cells and something called the gap junction in between, where people understand where if the gap junction doesn't work the way that you'd expect it to, hearing doesn't work the way you expect it to. These papers are really recent. The paper that discusses this is from 2022, and doing things like in vitro experiments on the cochlea was first published in 2005. So all of this is relatively recent. The key part is that based on experimental data, we can model an auto gain control really well. And this is in particular the key for really allowing us to hear between, the 30 to 120 decibels. There are papers and experiments that show that in mice that don't have Preston, so where they've been bred or engineered to not have Preston, they lose something like 50 decibels of hearing. So this is one of the main bits, if not the main way that we control for different loudness understanding. The inner hair cell, in particular, it's discussed in detail in chapter 18. So I'm not going to go too in depth in here. It's actually amazing in its own way. The simplest model is a half-wave rectifier, but that's not quite right. And it adapts really quickly to a large signal and then reduces gain to signal really evenly. It is the detection system. So basically it takes the basilar membrane movement and then detects that and then sends that onwards. I feel like I'm not doing it justice. In particular, it doesn't express Preston. So it doesn't have the same amplification concept. So stepping back a little bit, the cochlea is a three-dimensional spiral. And these are, well, let me take a step back here. This is a different view of slicing the cochlea. And you can see that the bottom of it, which is the basal end of the cochlea, spirals up 2.5 times to what's known as the, and Dick, I'm probably going to mispronounce this, the helicotrema, which is the apical end, which is the low frequency end. And throughout the cochlea, the shape, the width, and the flexibility of the basilar membrane all change, as does the shape of the actual cochlear scalas themselves. And so they do this so that I'm going to introduce a word in here. They're all tonotopical, meaning that certain areas or particular parts of the cochlea resonate best with a certain frequency. And you can see this exaggerated figure from, or the high figures come first since they don't carry as well in a traveling wave along the basilar membrane. You can see the figure from the book in the bottom, which is also from the title of the book, of a picture of the cochlea. The left picture is a dead cochlea receiving a signal that's really loud and seeing the deflection of the basilar membrane there. And the other one is of a living cochlea receiving a much, much smaller signal. And you can see that they're both doing a lot. So sound waves travel faster and with less displacement than in fluid than in air. So air is easily compressible, but fluid isn't. And so what tends to happen in the cochlea or in a fluid is that rather than try and compress the air, the basilar membrane is flexed. So most of the energy of the wave, this is my understanding, the basilar membrane gets deflected at certain spots of resonance into the other scala. and then this causes a bulge in the return window, which is the round window of the cochlea. The basilar membrane itself obviously then propagates these waves, and the speed of the wave changes, and it changes the wavelength. And an active cochlea amplifies by hundreds of times. There's a figure from the book here of a passive cochlea on the left, and counting by the number of waves and the millimeters from the base, seeing at a number of different snapshots what the deflection of the cochlea can look like. On the right, we can see that with the amplification of an active cochlea, that amplification is well off the figure by several hundred times. So this is an active cochlea is a really meaningful aspect. We have to model things that way. Excuse me, I got a phone call and I had to cancel it. We can think of wave models in the cochlea in either 1, 2, or 3-dimensional. The simplest analog via the book is the delay lines in an electrical current. And we look at it where the simplest model can be where k squared is k time, or a different k, which is a constant, times omega squared, where k is the radians per meter and omega is the frequency. The problem with this model is that all frequencies propagate at the same velocity in this. And so then this typically predicts a wavelength that's very small and is outside of an accurate range at certain parts of the cochlea. In a 2-dimensional model, we can think about fluid moving away from the basilar membrane, where we add a separate dimension where h is the height from the basilar membrane. And at low frequencies, tan h is approximately equal to its argument. So this becomes like the previous version. And at higher end of frequencies, it's basically plus minus 1. And so we can think of this as either thinking about shallow water or deep water. And figure 14.8 is the most informative here. There's a lot of material in this book. There's a lot of material in this chapter, and 14.8 was the hardest figure for me to work through. But it basically says that at certain parts of the cochlea, that's where resonance is really maximized. I'm wondering if, Dick, if I've understood the figure correctly.
Yeah, this is a figure that I did back in the 80s when I was working with Carver on cochlear chips, and I wanted to understand the underlying wave mechanics better. So I basically analyzed 2-dimensional models with the k tench kh kind of proportional to omega squared, and I've added some terms to make the wave number complex, either lossy or active gain. Where you see the cusp there, there's the ki where it's minus ki on the left, it goes through 0, and there's plus k on the right. So if you have a signed variable that goes through 0, you can't just plot the log of it. You have to plot the log of the negative on one side. So that shows where the crossover is between gain happening and loss happening. And that's the point that determines the peak of the wave. So there's a lot packed into this figure, and it's just a particular 2-dimensional model with a particular formula for how the imaginary part comes into the dispersion relation.
Yeah, thanks.
Shows the boundary between the long wave region where the hyperbolic tangent function is about equal to its argument, and the shortwave region where it's saturated out at plus or minus 1. There's sort of a, it's not a sharp boundary, obviously, but that's the conventional boundary is where k times h equals 1. Call that the characteristic place for that 2-dimensional clear shape. Yeah.
3-dimensional models are typically modeled from experimental and computational parts, but that comes in later. The next part of the chapter is thinking about character or mapping the characteristic frequency that we've been talking about. The spacing of where in the cochlea certain frequencies are maximal or most resonant is relatively well understood. There's a frequency place map, and we've taken this from the book on the right-hand side. The right-hand side shows the 2.5 turns of the cochlea, and the inside is just counting millimeters. So the very outside is the entrance, and it's saying, we're 35 millimeters from the end. And then the frequency is on, or the characteristic frequency is on the outside of that. So the first number is 14,000 hertz. The circles denote the various keys of the piano. So you can see that the start of the cochlea just detects frequencies that are well above the frequency of a piano. But then we keep going through it. The understanding is that the spacing of the cochlea, and we can see this by looking at this map, is actually pretty even and good, where there's enough spacing between different keys to really place things well, except for the very end. So these are really low frequencies, where we can see that there's very little physical distance separating very low frequencies. We can also imagine that there's a lot of distance separating really high frequencies. This sort of matches with my understanding of how hearing, people say that hearing at really high frequencies is poor, and hearing at really low frequencies also starts getting poor. We can see also that the last millimeter is just really not spaced well. This is the helicotremor, and we can see that if we look at the Carfax model later, we'll see that we do different things below 20 hertz than we do above. This is sort of modeling this part. What else can I talk about with this chart? Yeah, the hearing of low frequencies, after chatting with Simon out of band, it turns out that one of the ways that we hear at low frequencies is that we're not just looking at the place in the cochlea, but we're literally looking at how many times do we get a signal from the basilar membrane. Sorry, how many times do we actually get a signal from the inner hair cell? So this chart is, or this figure is really interesting in here. The main takeaway for me is that at the really important parts of hearing, we have a really well-spaced range of, we have a really well-spaced cochlea, and at either end it becomes a little bit poor for different reasons, for different edges. So now we can think about this as a cascade. Obviously, the wave in the wave of sound travels along the basilar membrane. So we can model each position in the cochlea. So we can model, for instance, every circle if we wanted to in here. And we can model it as a cascade of filter stages. So we can model a single position in a cochlea and then inform further into it. To do this, we have to implement a rational transfer function, and we have to, and it makes sense, and this is based on a lot of details in the chapter, to use pole zero filter cascades, which we talked about in the previous chapter, and we'll have details in chapter 15 and 16. There's a sharp drop-off that's needed, because that's what we've seen in real cochleas. There's a significant delay, so obviously it takes time for the frequency to move along. What we can do is sample along the Greenwood map. So create a filter cascade where we take along this Greenwood map. And how many samples we take along the Greenwood map depends on the detail of frequency that we get in a discrete system, because obviously in audio and computers, we have discrete systems. We can see a real example of this for the cascade filters on the right-hand side, where the top images for silence And the bottom is after we hear the vowel A. We can see that there's a really beautiful reaction, and at certain points, there's a very steep drop-off. Let's talk about modeling this. I'm trying very hard to avoid talking about the CARFAC in chapter 15, but a lot of the goals are to keep things simple. The other goals are to model multiple things. So to model basilar membrane movement, inner hair cell output, and others, since they're all interesting to different groups. You know, if we can model the basilar membrane movement, then we can basically talk about ways to induce the movement in that basilar membrane that we want so that the inner hair cell responds appropriately. That's useful when, for instance, we're modeling ears or cochleas that don't have perfect outer hair cells. Modeling inner hair cell output is interesting for similar kind of reasons. Modeling the auto gain control is also interesting. And to make this parameterizable is also important because we want to respond to biology experiments and also simulations. Clearly, we want to do this in a discrete way because audio input is discrete, and we want to include an auto gain control model since that's crucially important. CARFAC in chapter 15 formalizes this. We basically model the basilar membrane, outer hair cells, inner hair cells, and auto gain control. That's the essence of it. There's further things in here where there's a binaural gain control. And this gets talked about later in, which one's the binaural chapter? I think it's chapter 19. I've forgotten the chapter number. But there's a binaural gain control mechanism. So in mammalian hearing, the gain control from one ear impacts what we do with the other ear. There's a beautiful figure on the right-hand side from 1985 showing the functional roles of inner and outer hair cell subsystems. And if I can use my mouse, we can see, for instance, that output from the inner hair cell goes to higher auditory centers. And then this comes back to a biomechanical gain control in the outer hair cells. This was understood in the 1980s. There's a lot of other details about various regions of, I've forgotten how to pronounce the OC, the olivocochlear neurons. Have I pronounced that correctly, Dick or Simon? Oh, Dick, you're still muted.
Nope, still muted. Olivocochlear is correct.
Okay, thank you. So this was understood in the 1980s. As my final slide, there's a much simplified figure that I made the other day, which is also beautifully incorrect. But we can think about the way to model a cochlea somewhat like this, where we'll have sound input. The sound input will move the basilar membrane, but we'll also go to the outer hair cell. This is actually incorrect, and I'll talk about why. The outer hair cell then amplifies and takes that signal and moves the basilar membrane, which then excites the inner hair cell, which then sends a neurotransmitter to your brainstem. And this comes back via an auto gain control to control the activation of the outer hair cell. This is a super simplified view. Why is this incorrect? Because in reality, what's happening is that the sound input is going into the basilar membrane. There's a shear action via shearing against a different membrane, which I've neglected to mention enough, the tectorial membrane, that actually causes the excitation of the outer hair cell that then moves the basilar membrane further. But for a super simplified view, I found this super useful. Further views in chapter 15 obviously go and introduce the cascade that looks like a much prettier and much more obvious version of this. But yeah, this was my extreme summary of what's a really in-depth chapter to modeling the cochlea. I think we have plenty of time for questions, and I imagine there are plenty of questions.
Thanks, Rob. Great presentation.
Thank you.
Julian, your hand is up.
Yeah, just a question on this last slide, actually. Was wondering whether that auto gain control, I mean, obviously it helps with interpretation of the sound because it allows for better dynamic range. Does it also protect hearing? Does it protect, is there some mechanism there that protects these ear cells from being damaged or anything like this?
So that's a really interesting question. I've learned a couple of things. One is that the reflex in the middle ear that we talked about earlier is one of the main protective aspects. And in fact, people, before they shout, reflexively activate that one so that it protects hearing from ourselves. Wow. The other one is, and I actually will answer, I don't know if the auto gain control in here is protective, but I remember seeing a paper, and I can find a link to it, in the last few years where they took two groups of people and literally sampled blood from two groups of people. The first group was exposed to silence for a while before they took a blood sample from people. The second group had headphones on hearing loud noise for a while. And it turns out that they could measure, there was an amount of Preston in the second group's blood that was higher. So there was a difference in there, which sort of indicates damage or something else. So I'm not sure. I don't know if Simon or Dick have other thoughts on this.
I never heard of Preston in the blood. That's interesting, but maybe that's getting knocked out of some hair cells by the loud noise.
Yeah, I'll find the link to the paper. I'm sorry I didn't link it in the slides. I thought about it, but I wanted to make the slides shorter instead.
Yeah. Super interested to hear about it.
Yeah. Julian, one of the theories about the outer hair cell gain control is that it's protective, in particular by people that don't think the active gain theory is right. It's not there about adding energy. It's there about subtracting energy. So you can look at the gain control as the thing that shunts excess energy or something like that. But I think primarily the way it works is adding energy to the traveling wave. There've been plenty of studies that have shown that, and the fact that the ear can emit tones when it goes a little unstable is pretty indicative of the fact that they can add energy to the traveling wave. David or Simon, I think you said something muted. David, go ahead.
Okay, so wonderful presentation and a lot of new insights from it. Thank you very much. I'm curious about the time constants that are operating here. You know, if we think about the automatic gain control like you would an audio compressor, how fast does the gain control kick in? Or are there multiple mechanisms of automatic gain control, for example, like the acoustic reflex that you get when you're shouting at someone or someone shouting at you? Is that on a different sort of time constant to some of the neurological mechanisms?
This is part of the discussion. If I'm remembering reading the chapter about auto gain control, this is definitely part of the discussion there. And my memory is that the answer is yes, it's slower.
Which is slower?
The auto gain control is slower than, like, it comes in at some time point later. Like it's not as instantaneous as some of the other inputs.
I think there's a couple of things to unpack here. The first is the stapedial reflex. So when you shout or make a loud noise in evolutionary terms, it's the loudest noise you're ever likely to hear. Notwithstanding, industrial society and firearms and things. But when we look at the evolution, the self-generated energy of a loud scream is the loudest sound you'll hear. And what you'll find is that the stapedial reflex is engaged 200 milliseconds before you make that noise. So this is an anticipatory reduction in the ability of the middle ear to transmit that energy into the inner ear. And basically what it does is by increasing the stiffness, by contracting, it increases the overall stiffness of the middle ear. Think of it as a resonator, and what you get is a shift in frequency up to the higher frequencies of the bandpass of the middle ear, which effectively means a significant reduction in the high energy of the low frequencies. So you're actually, Rob spoke about, this gain control that the middle ear can provide. This is one example of that gain control. So that's probably the most salient thing that you're going to see with, high levels of energy. Other thinking around the gain control working at the level of the outer hair cell is that, it could be operating, for instance, to help unmask a signal of interest so that, you differentially turn down the gain in areas that are off the signal frequency. Particularly important for unmasking speech or unmasking signals of interest with lower frequencies, because you get the so-called upward spread of masking. So, and that will have a different time course as well. That's a bit more contentious in terms of the discussion and debate around that mechanism. But the stapedial reflex is pretty well understood.
And that reflex with the 200 millisecond anticipatory onset, that's presumably for the person doing the shouting. If you were being shouted at, right, what's the delay between, hearing that loud sound and your receiver's stapedial reflex kicking in?
It's sometime after. I can't give you the exact milliseconds, but it's sometime after the onset of the sound, obviously. And so that's why the stapedial reflex is useless for defending your ears against gunshots and things like that, or snare rim shots and very loud, impulsive sounds, because all that energy has got in there and sort of mushed up the hair cells and the stereocilia before the stapedius has had a chance to do anything.
Wonderful, thank you.
So David, more generally, there's adaptation at all time constants, essentially, from very fast. There's what they call rapid adaptation, short-term adaptation, long-term adaptation, temporary threshold shift, and that's in addition to these middle ear effects, I think. Also in the middle ear, there's two different muscle systems connected to two different parts of the nerve. I illustrate that in one of the later chapters, I think. The stapedial reflex is mostly activated by sound. I'm not sure if what Simon described might have been more about the tensor tympani. That's the one that activates when you chew or speak. I think that's the one that's it's under voluntary control. If you practice, you can figure out how to activate that muscle. You can kind of hear it pulling, and you can turn down the gain of your ears voluntarily. Some people can. So
yeah, you're correct, Dick. I take that correction.
Yeah, I know Hong Lin has a question, but just before we move on, just in case anybody else has experienced this, sometimes when I yawn and I'm listening to music, the music goes slightly flat. I don't know if that's a thing that anyone notices.
Yeah. You're probably activating the tensor tympani. Yeah. Yep.
There you go. Thanks.
Not sure why it gets flat. It changes timbre, but I'm not sure.
It changes timbre, but it also sounds just a little bit flat to me.
Okay, let me think about that.
Hong Lin? I'm not seeing Hong Lin anymore, but he had a hand up. Maybe he's muted over there. All right, let's go to Xinhui for now.
Hi, I have a question about that picture which shows pressure wave and displacement wave, and then you have long wave region and short wave region. The first question is that x-axis is the place, right?
Yes.
That place seems a little bit shorter than later on you show the number. This is a 15 centimeter or something like that.
This figure.
Yeah, I don't remember what the units of X were on that and why it went to 1500. Sorry, I don't remember. It might be just sort of an arbitrary scaling where, well, it looks like I put 1000 at the wave peak for some reason, or no, at the cutoff place.
So this is like a response to maybe one single tone. Is that right?
Yes, it's a fixed frequency function of place. Yeah, it says omega equals 1. So this isn't a model where the characteristics of the place scale, the characteristics of the wave scale exponentially with place. So it's like a perfectly scaling kind of model. It's not based on a actual Greenwood map or anything like that. So it's kind of arbitrary or abstracted.
So I'm trying to understand what's the real difference between, what's the insight between long wave and short wave?
Mm-hmm. Yeah, it's basically the product of k times h, h being the height of the scala, assuming it's a rectangular cross-section box, and k being the wave number in cycles per meter or radians per meter. So the per meter times the distance in meters makes a non-dimensional value there. So, and that's the argument of the hyperbolic tangent function. So it needs to be non-dimensional. So 1 is sort of the conventional boundary between where the hyperbolic tangent function gives you approximately its argument for small values and approximately plus or minus 1 for large values.
Thanks.
I shared in the chat the paper that I found about noise exposure and blood levels of Preston, for those that were interested. And we've got Hong Lin with a question.
Yeah, Hong Lin.
Thank you. Thank you for the awesome presentation. My first question is a small point, which is the last graph, which is show the structure. I just say there's a direct arrow from sound input to outer hair cell. Should the arrow be from basilar membrane to outer hair cell? Right? I just wondering whether that's more rigorous, because I think the signal received by, yeah. Another thing is, this lecture reminds me of an old question when I learned this, which is, I don't understand why the ear, what's the scala vestibular has to, go way through the apex and then go back to the base.
Okay.
Right. It seems like only one side of the tube that really works to trigger the, to carry the or vibrate the organ of Corti. Why has it to go back? So maybe there's some physical reasons to make it easier to vibrate, but considering the vibration should be very, very small. Yeah, what could be the possible reason?
So, and then turn your mic off. Yeah. Hong Lin and I are actually in the same room, and through Teams we have an exciting mic on and mic off situation. Yes, I mentioned this when I showed this figure, that this is in fact incorrect, this figure, in that what actually is happening is that the sound input goes into the basilar membrane, that then becomes input into the outer hair cell, that then amplifies the basilar membrane's movement. I found it useful to think of it this way instead, and just ignore the tectorial membrane. Yes, in fact, this figure is incorrect. It's a gross oversimplification. So that's the way it is. Your second question, I can't pretend to be a biologist, but I think my understanding, I'm going back to the figure. So the question is, why is there a connection at the apical end of the cochlea for the two elements here? And why isn't the part right at the end here like a sealed membrane? I guess I don't have a biological reason, but I think this makes it easier to equalize the liquid pressure on both sides, in that when there's a basilar membrane movement at one point, it shifts the fluid on the other side more easily. And I think at the apical end, it becomes even simpler, like for very low frequencies. I'm sure others on the call have a better understanding.
Yeah, I would say the physical reason is just to make sure that there's no average pressure difference between the two sites. If you look at what happens when a sound wave propagates down there, for any frequency above 20 hertz or so, the wave doesn't make it all the way to the helicotrema. So there's no motion there. The fluid is sitting perfectly still. It's just there's a hole there so that there won't be a net pressure difference. So the basilar membrane won't be bent out one way or the other. It won't be bent up or bent down on average. It'll be sitting in its comfortable, relaxed, sensitive position.
I see. Thank you very much.
So just to clarify on that point, if you can, so Dick, you just said there is no movement through that point at all.
Right.
Then if there's no movement, how does it bring value?
Well, there's no movement normally in response to sound. There's only movement if there was a pressure difference, a little bit of fluid would move to relieve that pressure difference.
Sure. So there's short-term or instantaneous movement, but there's no average movement. Or you're saying there's not even instantaneous?
Well, it doesn't need to be instantaneous. It just needs to work in the long run to be equalized. So at frequencies that are low enough, the wave will get all the way down there. Like if you're listening to 5 hertz or 10 hertz, you may not experience that as a tone, but you'll kind of feel it, and there'll be a little bit of movement up and down, a little bit of fluid oscillating back and forth through the helicotrema. But at higher frequencies, the fluid gets from the oval window back out to the round window, not by going through the helicotrema, but by deflecting the membrane, taking a shortcut path like those arrows that are shown there that kind of
right. So there's a compensatory deflection. If there's a deflection down at the basilar end, there's also a deflection up, so that there's no net pressure difference from one side to the other. Is that the right understanding?
It's if you look at the oval window being pushed in,
yep,
and the round window being pushed out,
okay,
that movement is compensated by the bulge in the membrane. But it's not just a single bulge, it's a bulge that's moving with frequency, but the net amount of bulge has to compensate what the windows are doing, unless the frequency is so low that the wave affects the fluid at the helicotrema.
Okay, thank you very much for that.
Mm-hmm. The helicotrema it's a more complicated bit to model, because we normally assume that all the energy in the traveling wave is propagating forward and that it doesn't reflect, and that's known not to be an accurate model because we can detect stimulated otoacoustic emissions, but most of the energy is moving forward. A little bit reflects out and you can detect it, but in terms of the primary function of the cochlea for detecting sounds, that reflected bit that comes back out doesn't seem to be important for anything. It's good as a diagnostic tool for figuring out what's going on in the cochlea and making theories about exactly how it works and so forth. But at the helicotrema, if the frequency is low enough, the movement of fluid through the helicotrema equalizing the very low frequencies can be thought of as a reflection. It's like it's a electrical delay line or electrical transmission line that's terminated in a short circuit. You're going to have on average, no voltage across that thing, and at very low frequencies will reflect back as a negative voltage wave and cancel, so that you get zero across there. So to model the very low frequency behavior, you kind of have to acknowledge that there's a reflection at very low frequencies from the helicotrema, and we have kind of a hacky way to model that.
I think David's got his hand up again.
Dick, you mentioned the term otoacoustic emissions before, and it's been mentioned in this series elsewhere. And I'd really love to understand a bit more about that, because my naive understanding is that the ear somehow itself emits noise, sound. I just can't get my head around that, nor can I get my head around how that might be measured. So I'd love to know a bit more about that. It's been mentioned a few times.
Yeah, and I don't remember all the names and dates, but there was someone maybe in the late 70s or early 80s that observed certain people, their ears would have spontaneous otoacoustic emissions, tones basically, that would come out. He said he had one family that had this so bad you could hear their ears emitting a tone from across the room. He didn't need a sensitive microphone to detect it. They're just like blaring out sound. Some people who have tinnitus, mostly tinnitus is kind of an inside the brain effect that happens in regions where the cochlea is not delivering any signal, where you used to have some signal and the brain kind of hallucinates something. But there's another form called objective tinnitus, where there's an actual sound ringing in your ear that you're hearing. It's actually your ear emitting a tone, and it hears it and also emits it. And I get this from time to time, and when it happens, I can hear one of my ears suddenly makes a tone, and then it adapts, and in a period of 10 to 20 seconds, typically it squelches it. But some people have it persistently. So just, the fact that these spontaneous tonal emissions exist suggests that there's a traveling wave amplification going on, and there's probably some point defect in the cochlea that causes a significant reflection rather than the forward wave moving forward as it's supposed to. Enough of it gets reflected back through the amplifying region and then bounces off the window again, that you get this kind of laser-like resonance with amplification that causes it to emit. So not everyone has, well, at very low levels, it's possible that everyone has this, but more common, I think, and easier to measure, what they call evoked otoacoustic emission, where you can like play a click into the ear and look at what comes back. And it can often excite a bunch of discrete resonances that are generally thought to be associated with irregularities in the cochlea that cause certain points to be more reflective than others, and cause these patterns that some say they're as distinctive as fingerprints, or sort of like that your ear has a particular pattern and you can characterize it that way. You can also do emissions with tones, like if you put in a pair of tones about 20% different in frequency, you can pick up the cubic distortion tones that those cause. And that's used as a diagnostic tool to see if your outer hair cells are working. You can use it on infants. So there's all kinds of different ways you can pick up sounds coming out of the ear and infer things about what's going on inside.
So yeah. I'm aware of hearing tests where infants would be presented with a series of clicks, and measurements are made of the auditory brainstem somehow. Yep. And that kind of makes sense with this idea of like a feed forward path of the stimulus. But I gotta say, it's quite surprising to think that you can also play a series of clicks and detect for some amount of time afterwards an actual acoustic emission from the cochlea, how long do those emissions last for after the stimulus has finished?
Yeah, well, some of them can be high Q resonances that last many milliseconds. It just depends.
Okay.
I have an interesting anecdote there. David Kemp was the first to observe the acoustic emissions working out of the Ear Institute in London. I was doing my postdoc years at Oxford and went up to visit, not him, but to visit Pat Wilson and Ted Evans at Keele University. They were also doing some recordings. And they recounted the experiment that they'd done just the week before, where they were testing out a microphone to record acoustic emissions in each other's ears. And so Pat Wilson was in the anechoic, the soundproof chamber with the microphone sealed in his ear, and he came out, and Ted said to him, "Do you realize you've got a whistle at about 1200 hertz?" And Pat went, "No." "Oh, yes, I do." And he heard that for the rest of his life. So, we have mechanisms in the cortex of suppressing the perception of some of these things, which also means that, sometimes you got to be pretty careful about what you tell your subjects in physiological and perceptual experiments.
I had a visit to Ray Metis's lab at Sussex some years ago, and he took me into his quiet chamber and demonstrated his quick audiological assessment techniques. And one of them was to play tones and measure the cubic distortion emissions. He quickly measured me and said that, yeah, your outer hair cells are really not working above about 2 kilohertz. He said my hearing was somewhat worse than it should be for people my age. And, I've only gotten older since then, but I don't think my hearing's gotten worse. So maybe it's about right for my age by now. I'm catching up.
We had a question from Xinhui.
Yeah, I have a question about the bone conduction speaker, how it works. Is that still through that oval window, or the signal can pass to some other place to make people perceive that sound?
Yeah, the bone conduction is, I'm not sure how well understood that is, because, the bone is very hard and stiff, and so you don't get a lot of compression. You're not like squeezing on the size of the cochlear chambers much. There's not a lot of motion, but somehow there's enough that the fluid moves, and you can get a differential movement between the two windows, between the round window and the oval window, because one of them's loaded by the stapes and the other one's just fluid. So since the windows have different impedances, if there's anything that's changing the pressure in the fluid, it'll cause a differential motion at the windows, and then you'll get a traveling wave propagating from there. So I think I saw an experiment somewhere where someone drilled a hole near the apical end of the cochlea, put some kind of a pressure piston driver thing in it, and driving, near the apex, you still get a wave propagating from base toward apex. The wave doesn't start where you're putting the pressure in. It starts where you get the differential motion of the two windows. And I don't know, that doesn't explain exactly how bone conduction headphones work, but it's, yeah, someone might know.
Thanks.
I've always got questions. You just need to tell me to shut up and you're tired of them.
If I see any other hands, I'll tell you to shut up. Otherwise, go ahead.
Yeah, do that. So this is it's not a cheeky question, but it's for the Australian Future Hearing Initiative. Because I'm thinking that at least the intent is to look at ways to improve sound perception for people who have certain kinds of impairments. I'm thinking that the fluid and mechanical system of the cochlea only permits certain kinds of stimulus. Whereas if you, say with like a cochlear implant, you're applying an electrical stimulus, you can do something like stimulate not just a place, but a place at a certain rate. So I guess the question is, like, you know, thinking in acoustic terms, it, like, you know, in some ways, we've got one hand tied behind our back about how we can sort of like change the acoustic stimulus to make up for deficits in the cochlea. Whereas, you know, if you look at direct electrical stimulus, that, you know, opens up some opportunity.
Then you have the other hand tied behind your back.
Yeah.
Yeah, they have very different limitations.
Different limitations. So that's only just become apparent to me at this lecture today when I, you know, just realized about the, you know, the entangled nature of the mechanics and the fluid side of things. Do people have any thoughts in response to that?
Yeah, you know, there's all kinds of different strategies people use in hearing aids and cochlear implants, and different theories about what might help, and you know, what processing to do and how to adjust it, and so on. So one of the things we're trying to do in the AFHI first project we're working on, called hyper-personalization, is by trying to fit a personal model of a person's hearing or impaired hearing, and then use that to optimize the parameters of whatever processing algorithms you have that you think might help. Or the goal is to try to find, you know, can we adjust the thing to make the net result closer to normal, whatever that means. And so there's a lot of open-ended parts to that, like how do you measure close to normal? What's the appropriate loss function for optimizing here? And you know, what are the different processing strategies that you can parameterize that will help you do that? And what tests do you have to make on an individual to make a comprehensive model of their hearing? You know, we can start with just an audiogram, but that obviously is not enough to motivate all the potential adjustments that someone might want to do in a hearing aid. But it's a way, it's how we're starting to sort of build a closed loop system around sort of fitting conventional hearing aids with conventional hearing tests. And then once we have that framework, we can start adding features and adding tests and trying to figure all that out. So yeah, we're trying to do what you suggest. We're trying to do it in parallel on acoustic hearing and electric hearing with the same framework. So there are actually some hybrid aids, I believe, where you can have a cochlea that has intact low frequency hearing and also electric hearing for part of it. And, you know, to jointly optimize those is, it's a very interesting problem. And to do that with a human in the loop saying, yeah, I think that might be better, that's pretty slow. But if we can model the human's hearing well enough, then maybe we can do the optimization quickly by computers and give them a better setting to try out. Those kinds of things. It's building the framework to where we can work those problems.
Has consideration been given to the possibility of altering the incoming signal frequencies? So if, you know, for example, you had poor low frequency perception, maybe you could upward shift.
Yeah, it's almost always going the other way. They have in commercial hearing aids, there's often a frequency lowering option where you can You take the top octave that you need for speech and sort of down modulate it somehow into a narrower bandwidth. And one of the, actually, there was an Australian guy that did a lot of work on this. Hugh McDermott has kind of made that a large part of his career in hearing.
I think it's worth emphasizing as well that using something like CARFAC, which is one of the reasons that, you know, we're focused on this, we're starting with a model of hearing that is orders of magnitude more sophisticated than the model of hearing that drives current hearing aid signal processing design. You know, current signal processing in hearing aids is a very blunt instrument. It does gain over some small number of channels, and it does compression over a certain level. That's all. And as we understand more about CARFAC and we understand more about the parameters that are exposed in the model, it gives us a much more sophisticated palette to work with. I think the other part of this as well is that using machine learning, you know, ML is ideal for searching large problem spaces and with enough data, finding unique and novel solutions. So, you know, our first target with hyperpersonalization is, okay, let's see if we can just do as well as the current state-of-the-art fitting formula, like, you know, the NAL, NL1 or NL2. But, you know, we're anticipating that we should be able to go well beyond that in terms of our capacity to tune the signal processing to the parameters that we are now modeling in Dick's model. But also then, as Dick pointed out, you know, people don't present with, you know, hearing loss isn't one thing. You know, it has a variety of different and sometimes quite combination of causes, and you know, this gives us a tool that gives us the potential to address the individualization of the causes of a particular patient's hearing deficits.
And is consideration being given to the situational aspects of sound perception? Because I know in certain situations, I would love to be able to, you know, EQ what I'm hearing, or, you know, change what I'm hearing because of where the information content lies. And this, you know, issues about masking like that, you know. So
yeah, that's actually the second half of what we're doing, ecological testing and control. So, you know, we're looking at it both from the instrument that's put in the ear and the context, environment, and intent of the listener.
Great.
Mm-hmm. More questions, anybody? Okay. Well,
not a question, just a comment. I put it in the chat. I thought this was great. It's so important that we can join the dots between the maths and the physiology, and we can come up with fantastic mathematical explanations that actually don't mean anything until we can link it back to what's going on physically and in the physiology. I thought this was really great. So thank you.
Yeah, thanks. Appreciate it, Greg. Thanks again, Rob, for a great presentation.
I had a lot of fun preparing for it. I don't know if that's obvious from my presentation. I read a lot of papers outside of the text and really dug deep into it. Yeah, it's a good introduction, and I think this chapter sets the stage for all the future modeling chapters. And so I think next week is the chapter about CARFAC, where we learn about.
Yeah, I think Miriam Hosseini next week will present the CARFAC overview chapter. Look forward to that one. Great. See you all then.
Thanks. Great session.